Hello everyone. I'm Xianrui from the University of Hong Kong, and now I'm going to talk about our work, BlindHub, Bitcoin-compatible privacy-preserving payment channel hubs supporting a variable amount. This is a joint work with Shimin, Arash, and Mirzaei, Zhimei, Oguzhan, Ersoy, Amin, Sakzad, Muhammed, Esgin, Joseph Liu, Jiangshan, Yuen, and Yuen. Bitcoin is a pioneering cryptography. However, its weak scalability could not satisfy the increasing demands of the developing Bitcoin ecosystem. And there are several solutions to scale Bitcoin. In this work, we focus on payment channel. And payment channel is regarded as one of the most promising solutions for addressing scalability problem. It allows for a limited off-chain payment with only the channels opening and closing transactions recorded on the blockchain. However, it is financially infeasible to build channels with everyone. So payment channel network is proposed to provide a partial solution to this problem. It allows users with no channels between them to pay to each other via the channels of some intermediary. However, payment channel network require routing and active participation of parties. Payment channel hub, as an alternative, deploys a star topology, and it allows users to pay to each other via a single intermediary. In this work, we focus on a secure and privacy-preserving payment channel hub. It should satisfy the following security properties. The first is atomicity, which requires that either Alice receive M coins from hub and hub receive M coins from Bob, or both parties receive none. The second is relationship anonymity, which says that the hub should not learn who is paying to whom. The existing constructions of Bitcoin-compatible payment channel hub that can achieve relationship anonymity should either run the payment system for multiple times or running multiple payment systems simultaneously, which is not that flexible. The third property to satisfy is interoperability, which says that the payment channel hub system should support as many cryptocurrencies as possible. In the state of art, there are some works such as A2L and Tumblebit, which can achieve Bitcoin compatibility, relationship anonymity, and atomicity. However, these works require the payment amount to be fixed, which is not desirable in terms of security or privacy. Bot, on the other hand, can provide a flexible payment. However, and it is also atomic and relationship anonymous. However, it is not Bitcoin compatible. And in this work, we propose a solution which can achieve all the above properties. Now, let me introduce our solution. To circumvent the fixed amount limitation, our idea is to directly hide the amount. So we propose a new channel scheme which we call BlindChannel. To explain the idea of BlindChannel, let's first recall how normal payment channel works. Suppose now Alice and Bob share a payment channel, and now Alice is going to pay Bob M coins. After the payment, their balance are updated, and they are both aware of the updated balance. However, there are some differences in BlindChannel. In BlindChannel, only one user can access the balance, while the other cannot. Again, now suppose Alice is going to pay Bob M coins. Instead of just informing Bob of M coins, Alice will just send a commitment of the amount as well as a proof, which proves that the amount used in the channel equals to the one in the commitment. For the ease of presentation, we call this proof as amount consistency proof. After the proof, Bob will blindly sign the transaction to enable the validity of the transaction. After the payment, only Alice, and now Alice can still see the balance, updated balance, while Bob can only see the updated commitment of the balance. To further explain the idea, let me show a simple example of payment channel hub in the BlindChannel setting. Now, Alice is going to pay Bob through this tumbler. So in the first step, Bob will send a commitment of the amount to Tumblr as well as amount consistency proof. After that, Tumblr will blind sign the transaction so as to pay Bob. Next, Bob will share the commitment of the amount with Alice, who will use it to perform a similar payment to pay the tumbler. So this is a simple payment procedure in this simple construction. However, this is under the assumption that all the users are honest. So suppose now Alice is malicious, then Alice can just refuse to pay the tumbler, and so we will, as a result, we just lost the atomicity. To achieve atomicity, we need some the building blocks. So first, let me introduce a cryptographic primitive called adaptor signature. Adaptor signature is based on digital signature and hard relation. It works as follows. Suppose now Alice, in the first step, Alice will generate a pair of statement and witness from a hard relation, and then she just send this statement and the message to the signer, who is Bob here. Then Bob will just use this statement and his secret key to generate a pre-signature on this message. Here, this pre-signature is essentially an incomplete signature. Then Bob just sends this pre-signature to Alice, who will then verify the validity of this pre-signature. After, if this pre-signature is valid, then Alice just adapt it to a full signature and publish this full signature. At this time, Bob can access this full signature and just extract the witness from the pre-signature and the full signature. Based on this primitive, we introduce a new cryptographic primitive called blind adaptor signature. Blind adaptor signature is similar to adaptor signature, except that Alice, instead of just sending the message in plain text, Alice will send a commitment of the message as well as a proof to the signer. And signer will just sign on the commitment instead of the message. So based on this new primitive, let's see how to achieve atomicity in our example. So after Bob's amount consistency proof, the tumbler will firstly generate a pair of statement and witness, and then use this statement to generate a blind adapter signature on the transaction, so as to perform a conditional payment to pay Bob. Next, Bob will share this commitment of the witness and the amount with Alice, who will use them to perform a similar conditional payment to pay the tumbler. Finally, the tumbler will use the witness to release the coins in the conditional payment. So this is how we achieve the atomicity. And now let's look at the privacy. If we look closely, we can easily see that the tumbler can easily link Alice and Bob through the commitment of the witness. To address this issue, we need two other building blocks. The first is randomizable puzzle. This is simply composed of two components. The first is commitment, and the other is the ciphertext. And we can randomize the commitment and the ciphertext using a single randomness. And here, the encryption scheme is required to be a linear-only homomorphic encryption. The other is randomizable signatures on randomizable commitment. It says that suppose now you have signatures on two commitment, then you can firstly randomize the two commitment, and then generate a new signature on this randomized commitment without using the signing key. Using this, with these two new cryptographic primitives, now let's see how to achieve privacy in our example. So in the first step, Bob will perform amount consistency proof. Next, tumbler will generate a pair of statement and witness. And besides, tumbler will generate an encryption of the witness and then send them to Bob. And at the same time, tumbler will also generate a signature on these two commitments so as to link them together. And next, Bob will we call these two steps and puzzle promise phrase. Next, Bob will randomize these commitments and ciphertext. Besides, Bob will also randomize the signatures on these two commitments. Otherwise, the tumbler can still link Alice and Bob through these signatures. Then Bob we just share them to Alice, and Alice we just use them to perform a similar conditional payment with the tumbler. We call this step a puzzle solver phase. So finally, we should consider griefing resistance. Griefing resistance is about to resist griefing attack, where a malicious receiver will start many parcel promise phrase with the tumbler. In each of them, the tumbler should lock some coins. However, the sender would not help the tumbler to release the coins, and as a result, the tumbler's coins are just locked. To address this issue, we require all the users to register before the payment. Simply speaking, the registration works as follows. Firstly, Alice will generate a randomizable token and commit it and just send them to the tumbler. Then tumbler will generate randomizable signatures on these two commitments so as to link them together. And then the following part are just similar to the protocol we mentioned before. After achieving all these properties, then we can successfully construct a secure and privacy-preserving payment channel hub, which we call BlindHub here. We also implement our protocol. It takes roughly 17 seconds to finish a payment using our protocol. Since we use some zero-knowledge proof technique proposed quite a year ago, if we use some state-of-art zero-knowledge proof technique, we can further optimize the time to less than 10 seconds. Okay, and that's all our work. Thank you.
Thank you. Questions?
Hi, great talk. This is Ru from University of Waterloo. So I'm wondering, who is the client of this work? Like, who is the target client of this work?
What do you mean by target?
Who is going to use this architecture proposed in your work?
Since we just focus on the theoretical part, but in practice, maybe I think there will be some users that have such needs, but I don't know in practice.
And the next question is, how do you prevent it from being used by malicious parties?
Okay, good question. Since this work is kind of like a mixer for Bitcoin, but actually, if we just use it in practice, then maybe it will cause some illegal issue. But maybe in the next step, maybe we will focus on some compliance part on this line of work. So I mean, in practice, we will add some more things in this such kind of protocol to make it friendly to compliance. Yes.
Okay. Thank you.
Hi, great talk. Do I see it correctly that the hub samples a statement for the particular execution?
Sorry?
So user sends a commitment of the message, and the hub samples a statement for the pre-signature, right?
The hub
Tumbler, yes, in this case, Tumbler.
Generate per signature, yeah.
Yes, and is a pre-signature, can it be thinking of arbitrary hard relation, or do you fix it to some kind of hard relation?
What do you mean by fix
For example, do you fix it to D-log, or is your protocol working with arbitrary hard relations?
Yeah, fix on the statement generate at the beginning, yeah.
Okay, thank you.
Quick question. Great talk, thanks. I have a question about the blind channel concept.
Okay.
So you mentioned that one endpoint knows the balance, the other one doesn't. The one that doesn't know the balance, can they close the channel or not?
In our construction, we set a time lock which means that the channel will close after some time. So actually, but before the time lock, the time lock could not close the channel by itself.
Okay, so the channel has a limited, so to speak, a lifetime.
Yeah.
Okay, thanks.
Okay, I think we'll take the next question offline because we're running out of time. And let's thank the speaker again.